All right, so we're going to continue with trees and tree-based data structures. Remember, our overall goal here is to find a data structure that offers basic CRUD, that we can put stuff in, we can retrieve stuff, we can delete things, right? Such that all of the operations are going to be efficient, ideally log n here, right? We've progressively added more and more structure to this data structure, right? We started with a graph basically, and then we said, well, what happens when we do just a tree? That makes it simpler. That means that there are no cycles. That means that we can then orient it, right? And then we can start putting data in it left to right, top to bottom. We limited the number of children to 2 to give us binary trees. What we're going to do now is we're going to limit it even further and to give us something called binary search trees, right? Generally, when we will store elements in a tree node, but we can also impose additional structure on that data that it be ordered, okay? And that's what a binary search tree is. A binary search tree is where every node has a key element k, right? And every node in the left tree of k is less than k. Right? Every node in the right tree of k is greater than k. And this is really going to help us start searching because like binary search, when you cut something in half and you could ignore half of it, we're going to do that with our trees. If I go searching for something and I know that it's less than this key, then I need to go left and I can ignore completely the right because everything over in the right subtree is greater, right? This property holds for every node, right? Not just the root node, but every node in the tree. Property. There we go. Okay. All right, so for our purposes, we're going to simplify it even further. So simplification. For our purposes, all keys will be integers, right? Now, this is not that big of a deal because in practice, that's how it's done anyway. Remember, we briefly talked about the equals and the hash code method in Java, where you're generating these things. Well, the hash code method is there so that it can take any object, any user-defined object, and convert it into an integer. The hash code method returns an int, and that's because it's used in a lot of hashing. It's used in a lot of data structures that are hash-based. So this assumption is not that big of a deal. Furthermore, we will assume that all keys are unique, right? Because if they're not unique, then you can make them unique, right? We've already seen this with a database. If we have two things that are completely the same, like 2 invoices, exact same items, exact same date, exact same customer, exact same salesperson or whatever, right? This is why we covered using surrogate keys, the auto-generated primary keys, because there's always going to be a way to break ties, right? There is always a way to break ties, right? It could be a memory address. And then, in fact, that's how the hash code and equals method work. They, by default, they work off of the memory address of that Java object. It could be a surrogate key, a surrogate database key, right, etc. It could be an auto-generated UUID or whatever, right? Okay. So we're not going to allow duplicates, and they're going to be unique. Okay. All right. So there's the binary search tree property. Let's go ahead and take a look at an example here. This is the same tree that we had before, but instead of A, B's, C's, and D's, now we've actually got keys in this thing. Take a look at 50 and observe that everything in its left subtree is less than 50, strictly less. Everything in its right subtree is greater than 50. Right? That holds for every key. So if you focus on 20, everything in the left subtree is less than 20. Everything in the right subtree is greater than 20. Right? That holds for every single one of these keys. If it didn't, then we wouldn't be able to search it. Because how are we going to search it? Suppose that I was going to search for 45. Right? So I start at the root like anything else, and I'm going to search for 45. Well, is there any reason to go to the right subtree at all? No, because 45 is less than 50. So I will end up going left. And now we've got 40. I'm searching for 45. Is this the thing that I'm searching for? No. So where do I go next? I go right. And I find that it's right there. By making 1, 2, 3 comparisons, I've found the item that I'm looking for. What's the worst case scenario in this case? One of the worst case scenarios is finding 12, in which case I'll go left, because here I'm going to keep a counter on my fingers here, the number of comparisons that I make. 50, that's not the thing I'm looking for. Go left. 40, that's not the thing I'm looking for. Go left. 20, that's not the thing that I'm looking for. Go left. 10, go right. 15, go left. And 12, I finally found it. 1, 2, 3, 4, 5, 6 comparisons to find 12 there. Right? Let's see it in action. So what I've done is these visualizers are a dime a dozen. Again, let's search for 12 here and visualize how it's going to work here. Let's go ahead and find it. Right? Starts at 50, goes to 40, 20, 10, 15, and finally finds it at 12, making 1, 2, 3, 4, 5, 6 comparisons in the worst case. What's another worst case scenario? What if I were to search for, I don't know, how about 55? Oops, there we go. Is 55 in that tree? And this is the exact same tree as over here, but mine looks a little bit nicer, right? Is 55 in this tree? Nope. Where would it be if it were? Well, it'd be right of 50, left of 60, and you find here that it doesn't actually exist. So what does that look like for an unsuccessful search? Once again, right, left, and then you find that it doesn't exist because it didn't actually animate it, but you would have gone left after that 60 comparison there, okay? Another worst case scenario, what happens when we search for 13? Right, there we go. Something that doesn't exist, but it's all the way at the bottom of the tree, as deep as you can go. How many comparisons would I make then? 1, 2, 3, 4, 5, 6, and then you find that it doesn't exist because there is no right child of 12. So what's one observation can we immediately make about searching in a binary search tree? What's the maximum number of comparisons that you'll end up making? In this case, it was what? 1, 2, 3, 4, 5, 6. What relation does that have to the structure of this tree? It's the depth, right? The depth here is technically 1, 2, 3, 4, 5. So it's always going to be the depth plus 1 because you have to start out at the 0th level, right? So let's go ahead and codify that. How do we go about searching a binary search tree? Well, you start at the root, right? You make a comparison, and traverse either left or right, until you find what you are looking for. Sometimes you get lucky. What if I were to search for 50, right? Then I would only have one comparison. But sometimes you're going to get unlucky and have to go the entire depth of the tree. But otherwise, you find what you're looking for, or what's the other stopping condition here? You've fallen off the edge of the tree because 55 didn't exist, 13 didn't exist. So, or until you fall off the edge of the tree, right? In which case, it's an unsuccessful search. Right? Our observation here, is that at most there are d plus 1 comparisons are made. Right? Now that's great if you can guarantee that it's going to be order log n, right? The depth is order log n. But in general, it's definitely order d, right? Because d plus 1 comparisons is going to be order d. But we have no guarantee on the depth, right? Ideally, it's going to be d is order log n. There we go. There. There. All right. But in general, it can be the case that we've got d is order n. Right? In other words, it's going to be linear. That's that degenerate tree. We called that a linked list, right? So if it goes all the way to the left, then you're talking about a degenerate tree, and you end up having a linear depth, and thus a linear search again, because it's just it's nothing more than a linked list there. Right? Again, towards the end, we're going to talk about how you can get this guarantee, but we're not there yet. Right? Before we move on to the other operations, let's go ahead and start our design and implementation of this thing. So let me come over here and observe that we already have a binary tree, right? So a binary search tree is a binary tree. So I might be tempted to put this into an inheritance hierarchy. In other words, let's go ahead and create a new class here called binary search tree. Search tree. And I'm going to parameterize it as well. What if I had made the decision to extend binary tree? Because like I said, it is true that every binary search tree is a binary tree. It just has more specific properties on it. This property that everything in its left subtree is less, everything in its right subtree is greater. Right? But then think about what you're inheriting. You're inheriting a post-order traversal method here. Right? Does that make that much sense in the context of a binary search tree? Why would you want to do or a pre-order traversal? What does a pre-order traversal get you out of this? Pre-order traversal would be 2, right? Then what? A pre-order traversal would be 50, 40, 20, 10, 2. And then we would come back up here to 15, 12. And then we'd come back up here 24, 28, right? Something like that. Does that give me any structure? Does that give me any sort of advantage? No. What about an in-order traversal, by the way? Let's do an in-order traversal of this. Unfortunately, I don't have my iPad today, but we can do an in-order traversal of it. Right? So I would not process 50. Instead, I would process everything in its left subtree, and then I would process 50, and then I would process everything in its right subtree. Does that give you a hint as to what structure you're going to get out of an in-order traversal? What's the very first thing that gets enumerated in this tree here in an in-order traversal? 2. Then what? 10. Then what? We come down here, but before we do 15, we do 12. So 2, 10, 12, 15. Then 20. Then 24, it has no left child, so 28. Then 40, do you see the pattern? Why is it called an in-order traversal? Because for a binary search tree, it's in order. Right? So that would actually buy me something, and maybe I want to inherit that somehow. But a pre-order traversal, a BFS would be 50, 40, 60, 20, 45, 90. That doesn't make much sense. Right? Iterator pattern in the using a pre-order traversal, that doesn't make any sense either. Right? So I'm not going to lock myself into this hierarchy. Instead, I'm just going to say, no, it's a standalone binary search tree. Right? Because I don't want to inherit all that stuff that doesn't make any sense. It would cause my binary search tree to be somewhat of a leaky abstraction. Right? Oh, here's your binary search tree, and by the way, you can do this pre-order traversal over here. It doesn't do anything that makes any sense, but you can. Right? I'm leaking out information to the outside world here. So instead, the only thing that I'm going to take from my binary search tree is the fact that we're keeping track of the root, and that's it. And maybe the size. Private int size. Right? Okay? So let's create a constructor here. Public binary search tree. Right? And initially, I will say that the root is this.root is equal to null, and this.size is equal to 0, because that makes sense for a binary search tree of size 0. Okay. Now, we're not going to implement everything right away. We're going to do this in the simplest ones first and then the most complex ones last. But I do like to implement outline my interface. That is the public methods. We're going for a general data structure here, a general purpose data structure that supports CRUD. We want to be able to search and retrieve. We want to be able to insert stuff. We want to be able to delete stuff. So let's write methods, the interface, to do all of that. Public, add an element of void, add element of type T. Right? So it adds X to this binary search tree. Let's document it. Adds the given element X code to this binary search tree, BST for short. Okay. We're not going to implement that yet because we haven't talked about how to do that. But what we have talked about how to do is searching for something. Public T search TX. Right? So let me describe what this does. Searches this BST for the given element code X. If such an element exists, returns X. Now that doesn't make too much sense to begin with, right? Remember that we are simplifying this so that all of our keys and all of our data are going to be integers. But what is it? Does it make sense that I'm going to give you this element, 10, and I want you to tell me whether or not 10 is in that tree? And if it is, return 10. Right? I've already got 10. Why do I need to search for 10? It's because it's of our simplification. Right? Remember that, yes, we're going to end up doing just integers for demonstration purposes, but ultimately you're holding something of type T. Imagine that it's an invoice, right? And I gave you an invoice here, and I want the returned invoice, like you're going to be doing in your assignment 7 somehow, right? Now, I'm not going to give you the full invoice. Instead, I'm going to give you an invoice object with a particular UUID, or a particular total, or a particular salesperson, right? Those are called dummy keys, or sometimes they're called surrogate keys as well for that. But otherwise, this is note that X, the given value X, is actually a dummy key, right? With the proper search criteria set, but without perhaps all the data. In other words, just like we did with the book way back at the beginning of the semester, right? We created a dummy key that was just the author. But if I have a collection of books, I need a book as my key to search a bunch of books. I can't just have an author because these are books, this is an author, that doesn't compare. I need a book with the author set, but nothing else in order to search for a book with that same author, right? So X ends up being what's called a dummy key, and we return the actual full object, the full book, or the full invoice, or whatever, as a result of this. Right? So this does make sense to give this an element of type T and return an element of type T. Okay? The last one of CRUD, and we'll add more as we go along here, but public void maybe, delete element of type T. Right? And so this is going to remove that element of type T. So I want to be able to add stuff, I want to be able to search stuff and retrieve stuff, and I want to be able to delete stuff. You could add an update method, you could add a bunch of other convenience methods, and we'll do that as we go along here. But what I want to do now is I want to actually get that first one implemented. I want to implement search. We start at the root. We make a comparison on either traverse left or right until you find what you're looking for, or it results in an unsuccessful search. Right? I'm not going to be able to test it until we actually have this add method though, right? Because I'm not going to be able to get anything into that tree until this is all said and done. So what I'm going to do, we're going to test it later, but let's go ahead and implement this search. Right? Let's look at the first one. Let's look at compare to the root, right? Compare X to the root, I should say, right? To see if that's the thing that we're looking for. So is that the thing that we're looking for? X is equal to the value stored in the root. If it is, I will simply just return the root value, Now obviously this is not correct code. We're going to translate this though. Is equal to the value stored in the root. So the value stored in the root is what? This dot root dot get element, right? Okay. So X is equal to. How do we translate this is equal to? What if I did this? Equals equals. What does equals equals do in Java? What does equals equals do in most programming languages? It compares the memory address. That's not what you want, right? Because again, this is a dummy key, and this is what I actually want to return, right? They're obviously not going to be the same thing in memory, right? All right, dot equals. Remember that guy? Right? This dot root is equal to that, right? That tells me if it's equals, but what else am I going to want to check? Else if X is less than the root element, then where am I going to traverse, right? I'm searching for 42. 42 is less than this root element, so I need to go left. Right? So go left. Right? What is the only other possibility here? Go right. Okay? All right. So is equals going to give me an answer to those other two questions? Less than? Nope. All right. So if x is equal to, right? If x is less than the root element, and let me go ahead and copy that down here and immediately change that pseudocode into that. So what kind of a construct, what kind of an object have we looked at before that is going to give me an answer to, oh, this thing, the A and B, they're equal. Or no, A comes before B. Or no, they're out of order. B comes before A. What is that thing called? A comparator, right? So what else do I need as part of this binary search tree? I need a comparator because I've chosen to make this generic, right? I need a comparator that tells me these two things are equal, or this one comes before, or that one comes after, right? And I'll just call it CMP for short, right? Because a comparator will take those two things and return 0, something negative, or something positive, depending on the relative ordering of those two things. So I can't make that because is there any information about t in this class to determine what the ordering of t's are? No. You're going to have to give that to me at instantiation. Right? You need to give me a comparator by which to compare things. This .cmp is equal to cmp. All right? Now, there are built-in types like integers that are naturally comparable, but we're not going to cover how to do that. Basically, you'd have to check. If it's comparable, then I'll go ahead and use the compare to method. Right? But otherwise, we're going to use this comparator here now. So, is equal to. How do I do that? This .cmp compare those two things, right? X and this root. And remember that it returns 0 if they are equal. Right? So if x is equal to the root element, then it'll return 0, and I know that I've got the root value here. So let me go ahead and translate that now. Right? There. Okay. If x is less than, then what is this compare method going to return? Something what? Negative or positive? So x and the root, x comes before the root means that they are in order, so something negative, in which case you go left. Right? If we're wrong on this, of course, you could just go ahead and come back and, okay, we're wrong and fix it. Right? All right, so how do we go left here? Or go left. Right? I'm only doing this with the root value. Right? This is basically step 1 in the process. Right? I'm not always going to be comparing it to the root value, right? When I traverse left, I'm going to be comparing it to that node. When I traverse right, I'm going to be comparing it to that node. When I fall off, I want to make sure that I'm not comparing it to null. Right? So this is actually going to be in some sort of a loop construct. Repeat until ... until some action. Right? And I'm not going to always do it with the root. Right? So what I'm going to do is I'm going to establish a current node. Right? So tree node t current. I'm going to initialize that to the root. Okay? Because that's where I'm going to start. So repeat until some action. That probably tells me that I'm going to use a while loop or a for loop. While loop, because I don't know how if I knew how many iterations I'm going to go, I would know where it is, and I wouldn't need to be doing this, right? So while some condition here, we'll come back to that, I'm going to compare x not to the root, but to the current node. And if you find it at the current node, then you will return the current node. And I'm going to compare it with the current node, and if it's less, then I go left, and otherwise I go right. How do I go left? I update the current node to be current's left child. Right? How do I go right? I update the current to be get the right child, right? And I've gone right. When do I stop? Well, I've got one stopping condition right here, right? But that's already inside the loop. This will return from the entire method right here. When do I stop this entire process? Once again, search for 42. 42, right? Find. You go left, you go right, you go left, and you've fallen off the edge of the tree. We're in the nothingness now, right? What is the nothingness with respect to Java? Where is current going to be when you try to get that left child of 45 there? Null. So while current is not equal to null, then keep going. Right? Keep going left, keep going right until you find what you're looking for, or you need to break out of this loop because you have an unsuccessful search. What do we return in the case of an unsuccessful search? Can I return 0? It doesn't let me do that. Why? What's my return type? It's an object. 0 is not an object. What is the object that tells you it does not exist? Null, right? So let's put that into our documentation. If such an element returns X. Otherwise, returns what? No, null. Code. There. All right. I have no idea if it works or not, right? But you can clean it up a little bit there, right? Formatting it. I don't know how if this works because let's create a tree. Let's get rid of that binary tree over there. Let's go ahead and get rid of all of this. And let's go ahead and create a binary search tree for, say, integers. Right? Because maybe I want to recreate this tree and test it out on this tree. Right? So binary search tree, T, BST is equal to new binary search tree, except that I need to pass it in a comparator, right? CMP for integers here. That means I need to create a comparator for integers. Here's how we can do it. Comparator, this is a review from the very beginning of the semester where we created comparators for books and for authors and other things and integers, right? So here's my CMP for integers is equal to new comparator, right? And we immediately define what it means to be a comparator here, this comparator at least. So let's import that, great. And what you need to do is you need to implement this compare method that takes an integer O and returns something and returns an integer here. It takes two integers. Let me call them A and B. I don't like that the autocode generator does O1 and O2, right? But in any case, we've got A and B here, right? If A is equal to B, or dot equals whatever is equal to B, then we return 0. Else, if A is less than B, then we return something negative. Else, if B is, or A is greater than B, then they're out of order and we return something positive, just 1. Right? That was just to remind you of what the pattern looks like. Let's now simplify it. Remember that they're naturally ordered, right, in ascending order. So return A dot compare to B. Right? That'll return something negative, positive, or 0, depending on the relative ordering of A and B. Let's make this even better, right? Comparator dot natural order. There we go. So for any object that is naturally ordered, that has that compare to method, right? Integers, strings, whatever you want. If you want the natural order, then go ahead and just call that method right there. If you want the natural order but in reverse, not reversed, then you can do that as well. Right? Why do you not like that? Okay. That's odd that it couldn't be reversed, but whatever. Right. There's another way to do it. Anyway, pass that in. Oh, keys, integer. There we go. I can't do that. There we go. All right. Now, in order to determine if, say, 10 is in there, bst dot, what is it, search for 10, right? And let's print it out, system.out.println. BST search for 10, right? What's it going to return? Probably going to return null, right? Because nothing's in there yet. Of course it's going to return 10. So what I need to do before I am able to fully test this method is to actually implement this method. I got to get stuff in there before I can actually test to see if stuff is in there. So how do we actually implement this method? Let's come back over here. Suppose I wanted to insert 55. Right? Well, first of all, we need to make sure that it doesn't already exist. So let's search for it. 50, 60, 55. It doesn't exist. Right? If it had existed, though, where would it be? Right here where I'm highlighting. Right? What about 13? It's less than 50, less than 40, less than 20, greater than 10, less than 15, greater than 12. Oh, here, if it existed, then it would be right here. So does that give you a hint as to how you get things into the tree? You find where it should be, and if it's not there, that's where you put it. Right? You always insert it as a new leaf. Right? So how do you insert an element? You start at the root. Right? You do a basic search, which we've already done. Right? If the element, let's look at another indentation here. If the element exists, you could, what are my options then? Remember, we're not going to allow duplicates for our purposes. We're going to only say that it's unique. So if you do find a duplicate, what could you do? You could throw an exception. Right? You could quit out of the program in a tantrum, right? You could do what, though? What's the simplest thing you could do? Right? You could say, no, do no operation. No op, right? Is equal to no operation. In fact, we did this with a linked list, right? I think that I forget what we did with exactly with a linked list or an array-based list, but what we could do here is something in addition, right? We could also let the user know, right, whatever calling function is. When I say user, we mean the calling function, right? Know if it was successful or not, right? So let me come back over here to my interface. Initially, I made this into a void function, right? How could I reuse that return type there? Make it into a Boolean. Adds the given element to this BST if it does not already exist. Returns true, code, true if the insertion was successful, code false if it was not. In other words, it was not inserted due to duplicate. Right? Something like that, right? A better writer could come up with a better way of expressing that. Right? All right, so I now have my interface here. Right? We need to do a basic search. If no such element is found, then we insert it where it should have existed. Right? You end up inserting it as a leaf node where it should have been if it had existed. Right? You always insert as a new leaf node. Be careful though. You also need to keep track of the structure of the tree. When I insert a node, I need to make sure that it's connected to its parent, and I need to make sure that its parent is now connected to it. Because it's kind of like a doubly linked list where we've got references back and forth. Let's look at an example here. I want to be able to insert, what was it, like 42, I think is what we were doing. And that's going to be less than 50, greater than 40, less than 45, and insert as the new left node of 45, right there, 42. If I wanted to insert 13, I'm going to go all the way down to the end, find 12 that has no right subchild, and insert it as the new right child of 12. There. All right, so we'll talk about performance here in a second. Let's actually go ahead and try to implement this. Right. Okay. So I need to do a basic search, meaning that I'm probably going to have a lot of repeated code here. In fact, let's just start with that. First of all, if you find yourself cutting and pasting, not there. If you find yourself cutting and pasting, hold up and rethink. Is there a way that I could do this a little bit better? Right? We'll hold off on that for now though. Right? There's the basic search. If you find what you're looking for and it already exists, what should you do? Right? What did we put in the documentation up here? We're going to return false because we didn't end up inserting it. Great. Otherwise, we'll fall out of the edge of this tree. 13's not there. So we end up that the new node containing x should be at the current node. We found where it should be if it had existed. We can't return null here, okay? So what do? Can I say that current is equal to the new tree node of elements of type T holding x? I could do that, but does current have anything to do with the tree? It's a local variable. Right? All right. I need to insert it as this new node, right? Remember that it's a phantom node at this point. I can create a node, but how do I get back to my parent in order to make that connection between the new child and the new parent, and the parent? So let me go ahead and create this as a new tree node, T new child. Right? Okay. I've created the new node. Right? That means I've got this node sitting out over here. But now how do I get back to the parent? I've fallen off the edge of the tree already. Right? I should have stopped one step before I fell off the step of the tree, right? All right, so go back and completely rewrite this so that you're always looking ahead and stopping short so that you don't fall off the edge of the tree. Or keep this code simple and add more information. So if this is the current, I want this guy up here to insert 55. If this is the current, this phantom node that doesn't exist, but would if I had drawn it, right? What would you call this one up here? Previous. Right? We did this with linked lists too. Tree node, T, previous. I'll start that at null. Okay? All right, every time you go left, every time you go right, what should you be doing? Previous is equal to current, right? And down here as well, previous is equal to current, and then you can go on from current, right? Now the new node containing x should be at the current node. So what we're going to do is we're going to make previous point to the new node, right? Its child, right? And 2, make new child's parent equal to previous. That second one is really easy. New child dot set parent to be previous, right? Just like linked lists. And then of course you can return true. It had an effect, right? Couple of things that we're missing here though before we do the previous point to this new child, right? Actually, several things. If you add a node and you're about to return true, what should you be doing about the size? Just like we did with a linked list, keep track of it. This dot size plus plus. Okay? Now, how do I make the previous point to the new child? Previous dot set left child or set right child? Should it be that one or should it be the right child here? Right. Well, for 55, it was a left child. For 13, it was a right child. We're going to have to make another comparison here. So I'm going to steal this code. Right? There we go. So if the thing that you are trying to insert is is previous, there we go, is less than the previous element, then that means that you need to insert it as a new left child. Right? Else, we'll go ahead and set it as the right child. Now, why don't I need to worry about that equals here? Right? If it was ever equal, we would have returned, right? Okay. So I'm going to either insert it as the left child or the right child here. Okay. Now we can test it. bst.add 10. Right. Think it's going to work here? I'm going to cross my fingers, but it's not going to work. And we're going to find out why. Right? Null pointer exception. You cannot invoke the get element because previous is null. Right? I only tried to insert one thing. Do you remember with linked lists when you were trying to insert something into an empty linked list? That was one of those things we called a corner case, an edge case. Let's walk through this at least a little bit on what happens when this is when it's an empty tree. That is, the root is null. So, null and null. Does this while loop ever execute? Nope. We immediately come down here and create a new child, x. And then we try to compare it to the previous, which is null, because we never actually set it, because the root was by itself. How did we solve this with linked lists? We took care of this edge case by itself. If this dot size is equal to 0, or the root is null or whatever, this dot root is equal to new tree node of elements of type t x. Actually, I don't need to do that, right? And then return true. You had an effect. What else should you do? This dot size plus plus. Right? That's one of those edge cases. Let's come over here to the demo and see if it works. We add 10 and then we search for 10. Hey, it worked. Right? Is that all? We should probably search for 20 and 30, right? And are you going to find those things, 20 and 30? 10, 20. Oh, wow, it looks like it works to me. Right? Is that enough testing, though? Just because those things are in there, does that mean that you necessarily have a well-formatted binary search tree? Not necessarily. Let me go ahead and set a breakpoint here. Here's another way that you can use your debugger to test things, ad hoc testing, not formal testing. Let's go ahead and run this debugger and switch to our debugging interface here. Now remember, I've got my binary search tree. There's a comparator, there's a root, and then there's a size, which is now 3. That checks out. I can check out the root here, but it's just a tree node. But I can also expand it and look at the element. There's an element of type of 10 at the root. What about the left child? It's null. Okay. What about the parent? It's null. Right? Does this check out? Let's use the same visualizer over here. What if I were to insert 10? Then insert 20. Where's 20 going to end up being? As the right child of 10. 30. Where's 30 going to end up being? As the right child of 20. Right? That's what it should look like. So we've got a 10 at the root, and then we've got a right child. Expand that out. That's 20. It has no left child. It does have a parent, by the way, but it has a right child. I can expand that out. And its value is 30. So I've used my debugger over here to see, do I have the same visual structure over here? Right? When you go, there's another way that you could do this, and we've provided it in lab 15 next week. Right? Let me come back over here, and now that we've got these binary search tree here, we can go ahead and change and undo that, uncomment this. There we go. And unfortunately, what I'm going to have to do is I'm going to have to make this public for a second, actually package protected. What this is going to end up doing is it's going to take your binary search tree and it's going to generate TXIE code. TXIE is a part of LaTeX. Is anybody doing LaTeX in their 235 course? Yes? Okay, good. TXIE is an excellent drawing program and it allows you to visualize things, right? So let me go ahead and come back over here and output this tree as a string, but in TXIE formatting. So system.out.println bst, or what was it, tree utils dot to TXIE of bst. There we go. Right. And then I'm going to print that. Okay. Yeah, sure, whatever. Right. There it is. Now it's not very readable, right? But what you can do is you can take this over to any LaTeX editor and generate what it looks like. What's your LaTeX editor of choice for 235? Overleaf. Right. .com. There we go. I did this the other day. Right. And let me paste the new one. And it's going to be the exact same. But there we go. There. 10, 20, and 30. So I've got some level of assurance here that I'm actually keeping track of this structure here. Right? What would really help, though? Let's not do 10, 20, and 30. Let's do 10 random things. For int I equals 0, I is less than 10, I plus plus. Right? We can create random numbers using random. R is equal to new random. Right? Import that. And then bst.add r.nextInt. But let's go ahead and keep them small, less than 100. Right? Then I don't want to search for those. I could search for them. What would I expect? Most likely, unless I got really lucky, and 10 and 20 and 30 were all inserted, I'd probably expect null out of this, right? But let's go ahead and generate the TXIE picture of this. Right. Okay. And null, 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 so 10, 20, and 30, of course, didn't. That would have been like a 3% chance to get even one of those in there, right? Let's bring it over here and generate my picture again. Right. Recompile. All right. That look like a binary search tree to you? Oh, no? I mean, oh, sorry. Yeah.
Still counting.
All right, so 5. Is everything over here greater than 5? Yep. 87. Is 90 greater than 87? Yes. Is everything over here less than 87? Yep.
Yeah.
How about 37? 25 is less, 84 is greater, et cetera, et cetera. Now, it's not a very pretty binary search tree, I'll give you that, right? It's highly skewed to the right because our choice of the initial root here, 5. Most things 0 to 100 are going to be greater than 5, and so we're going to end up having a skewed tree way over here. So run it again. You get a nicer looking tree now. Oh, hey, looks like we got 30 in there by chance. Cool. All right. Let's go ahead and remove that one. There we go. And if you want to play around with this code, it is provided in Lab 15. Right? That's slightly nicer. Right? At least we've got one thing over on the left, right? But it doesn't look as nice as that one because I knew that I wanted it balanced for demonstration purposes, and so I knew to insert those in that order. Right? But otherwise, if you want to test it visually, usually what you can do is you can write code to generate some sort of map or like drawing of it. TXIE is not the most user-friendly thing that you can do because it's LaTeX, but it's the only thing I know of that does it well, unless you're going to use some visualization tool like this. All right, what else do we need to do? We still need to talk about how to delete things. We also need to come back and understand, well, wait a second, we've got a lot of repeated code here. Is there a way that we can collapse some of that repeated code, right? Is there a way that we could add other convenience methods? For example, we have search. What about this? Public Boolean contains, or Boolean contains, there we go, an element of type X, right? I don't want to necessarily retrieve it. I want to know, does it already exist? That would have been really helpful down here, or up here, I guess, right? If it already exists, just go ahead and return false, right? Otherwise, continue and try to find it. So we're going to have a lot more to do on the design and a lot more to do on the implementation of this binary search tree starting on Monday, or when we come back on Monday.